I will invite Prof. Dr. Ishamuddin Zainuddin to give his talk.
Sorry about changing my talk with Professor Nivas and Paul. I just had too many things to do, so you probably see will be reflected also by today's slides. Right. So today, actually, it's goes back. No, many steps to go from what we have done as one. Okay, I'm going to go back to the basic in some sense and mention about why this content information processing is now a big thing nowadays. Okay, essentially, physicists in the beginning always think differently in the sense of quantum theory. You have uncertainty principle, you have all these negative things that we don't understand about quantum mechanics. So it took quite a while to actually change the mindset of physicists to look at quantum mechanics in a different picture. Okay? In the sense that they start to think in terms like an engineer, okay, trying to make use of whatever negativity that people talk of quantum mechanics to be taken advantage and use it for useful. So it's like doing an engineering job in quantum physics, okay, or computer science. The same kind of, there's a different mode of thinking. Okay, essentially, quantum information requires a different kind of thinking, like design, okay, which was not really there in the beginning for physicists. Physicists think something nature, trying to find out something from nature and things like that. But here, you have to be okay. So today, as you can see, it's only two sections. Sorry about that. It's just going on at the same time, and probably too much for the same school. 6 lectures all together. Same school. So I thought that I'm getting myself into trouble, but never mind. I'll try my best to stay over. Okay. So the first thing is I'm going to talk about the elements of the information in quantum theory. And I'll talk about the information processing part, which I talked about. Again, towards the end, I'm rushing. Finish the slide, probably do that. Okay. So, in the beginning, I think we have actually mentioned this in school. One has to actually differentiate between the idea of state vectors, okay, which are elements of a Hilbert space, and these state vectors are the ones that has this superposition capabilities. Okay. And the simplest example is a cubic state vector. So you have a basis 0 and 1, just fixed. Instead of just 0 and 1, you are able to do any kind of superposition in 0 and 1, and that is also a cube. Okay? So it's not just the 0 and 1. When you cube it, it's also the linear superposition, the superposition of this basis vector. So why stop there? Actually, this is the simplest, just like we do classical computers nowadays, it's still on bits. So again, engineering-wise, it's easier to manage a two-state system. Okay? But you can actually generalize it to a D-state system. So you have basis vector from 0, 1 to B minus 1. Okay? So these are actually state vectors, but the quantum states are really defined as equivalence class of state with the relation of this when they are proportional to each other. Okay, so those are actually the ones called quantum states. So the quantum states really what we call rays, as mentioned last time. The idea of probabilities come in quantum mechanics are actually based on direction or signs. Okay, and they belong to actually not really, the rays are not, well, this quantum states are actually, if you think of these individual objects, they belong to this idea of projective space, which is the space of directions in H. Okay? So for a d-dimensional Hilbert space, okay, then we have the projective part, which is essentially the space known in mathematics for complex projective system. Okay? One dimension lower than. And one can actually try to, I think this is a rich area to play around with, because there are a lot of mathematical tools for studying on complex projective spaces, which has not been actually utilized by physicists right now. Let me just. So this is actually can be qualified by essentially the coefficient of the state vector, but those are not the true degree of freedom. The true degree of freedom is actually can only be defined locally on this vector space. When you sort of take the case of a local patch, this is like showing manifold, you just do a local patch and you try to define a particular coordinate system on that. So this will be the one for the case of a local patch for where Ci is not to 0. So you can actually form Z1 to Zd, but Zi is missing, so that actually gives you D minus 1, which is the actual degree system. So as you can see, you can only define it on local patch. So that means it's actually a nonlinear space. And of course, with nonlinear space, you can do simple. So this kind of thing are not really being paid attention too much, okay, because people tend to talk about quantum states and different scenario. Quantum state vectors another different scenario. So essentially, when we talk about operations made on space, all this quantum information processing, they are actually working on state vectors. So, while when they do measurements or trying to do discriminating between states, they are actually working on the quantum state, which is on the projective. So these two, sometimes people do not recognize. So there are some cases, because I'm trying to study this kind of things. So there are some issues about the complex projective space. So it can actually be described as a symmetric space, which is like a ocean set, okay, of un plus 1, un plus 1, that determinant 1, okay. And also you can also have this idea of vibration, that means you go 1 degree above, so it's there for CPN, so you can actually, this is related to the idea of block balls later on, okay. You can go to a higher dimensional sphere, and you have this line fibering out CPN. So this is actually known as the generalized bulk vibration. Okay. Now, it's also CPN is also a special case of what we call Planck manifolds. Looking at spaces of submanifolds Cn plus 1. So CPN is really think of this quotient set of Sn plus 1c over some isotopic group of some times. So you can see that you can think of CPN plus 1 being given Euclidean topology kind of thing, and then you can also do Zariski topology as opposed to get from proper symmetry. So that's go. So you can, the point I want to make over here is essentially that if you describe this as that, you can split this one there. You can use it as an action of n plus 1 on CPN, and you take it just like that. Okay, that's an action of n plus 1. And this is, related to how they do all this classification of entanglement, which I will not talk today, I'll talk tomorrow, but today I'll be doing something else. And one can actually use use the results for the special limit. Okay, so now you've seen the state vectors and the ways, but another way of actually representing the states, the true state, okay, is through the idea of the density operator. Okay, so for the pure states, the density operator is essentially the output product. Okay, and why I say it's representing the true state? If this thing is already normalized, so essentially there's only a degree of freedom left, which is a phase factor kind of thing. But the phase factor will actually cancel out from the cat vector and the graph. So it actually represents the true quantum state. Okay? And if you take the trace of rho, this is again, we have done bracket formalism of quantum mechanics is just the bracket psi, it is properly normalized, and the other thing that you can actually see from this is actually a projection operator. If you take rho squared with psi normalized, rho squared gives back to rho, okay, and of course you get a joint of this, just swap the line there, but it's still the same thing. So these are important properties that are density. So it's also convenient to introduce the idea of states, essentially to reflect the idea of partial knowledge of states under preparation. So when you do state preparation in experiments, you normally find yourself, you probably not get perfect state preparation. Okay, there is always imperfection in the way you do experiments. Okay, so it means there will be certain probability that is not in that particular state, the desired state. Okay, so you need to be able to actually include those kind of things into the formalism, and the idea of mixed state is also able want to do so. Okay, so what is it? Essentially, suppose psi I is just like this psi here. Okay, so there are several of them. So you can actually get a projection operator for the density operator for those pure states, and then give them weightage. For example, the desired state that you want to prepare, you can only prepare it to up to 90%. Then it will be the weight for that will be 0.9. Another 1% is probably things that you can't control in the experiment. Then you get weight 0.1 for the rest. Okay. So that is essentially this basically is the probability of finding the state to be that particular state. Okay.
Another question: how do you know the baseline of the pure state?
What do you mean by that?
Like because in the mixed states, you say in the experiment you have to actually know the different states at the different weights attributed to each state. So. Okay, that might
Okay, take an example. Okay, thing about, I'm just giving an example of that, it's sometimes not possible to have a perfect state preparation. With some states will not be the precise. Okay? But there are other things like, you prepare a particle in some energy states, but you know that that energy state might have different quantum numbers, okay? And we'll be able to know certain quantum numbers might be thinking of it is like a pure mixture kind of thing. Probably you want to assign half to one quantum number and then half to one quantum number. So again, that really depends on the situation that's been described. Okay, the other thing is, this is the properties of the sum of the totals. So what are the properties of the density operator? So again, it should reflect the one that is given by the projection operator. So the first one is the information property. And then it should be positive semi-definite operator. That means if you take the expectation value of that operator, it should be always greater than 0 or equal to 0 in some states. And the trace of rho equals to 1. Okay, this one for pure state will just give you the norm of that state. But in this mixed state, basically it corresponds to this sum of the probabilities. And then you have the trace of rho squared. In the case of pure state, it will be still equals to 1 because rho squared equals to rho. Okay. But for the case of mixed state, then usually you get fraction square, and then the fraction square will not add up to 1. So there's a nice thing when we talk about mixed state is that suppose this density operators belong to some kind of space of operators defined in Hilbert space. Okay. Then you find that that space is essentially convex. So you take any two in that particular space and then do this kind of convex combination. The result is always infinite. Okay. So this is really quite important for people to develop theories on mixed state. Okay, the other thing is the fact that for mixed state, the composition of the density matrix might not be unique. Okay? So this is just one snack of this kind of thing, and we can always find this number might go up in this operator might go up in a different language. Okay. So here is the cubic, the block sphere that Pranav introduced. So one can talk about the state vector instead. Okay. So here's the state vector, and it's properly normalized, and I've excluded one global phase vector out. So there's still a relative phase between the two. Okay. And I can parameterize the coefficients in this way, so that when you take the square of the modular square of the coefficients should give you the cos square plus sin square, which is actually 1. So essentially in this picture you can actually describe the block sphere as follows. At the north pole is actually your zero jet vector. The south pole is the south pole is actually the one orthogonal. So it's not really orthogonal in this sense, okay? But it's just a description. There's nothing really significant about the way it's been different. For the density operator, you can also associate this idea of block sphere. Okay? have to remember that it's not an operator, so you need actually to get the idea of block. That makes some sense to actually show you block sphere kind of thing. So remember that rho has to be Hermitian, and this is a two-level state, so you can actually get operators, Hermitian operators from the polymetrics. Okay, precise dynamic. Okay, so you get the Hermitian operators here, sigma I, polymetric, and then you can actually multiply with some coefficient. Okay, and that coefficient lambda, okay, is what we call the block. Okay. So what's good about this is that this kind of parameters is just another parameter. Okay. What's good about this is one determines what this lambda is, and actually determines the state. Okay. So, and you can actually get, theoretically, you can actually get this lambda by looking at remember that the trace of the density matrix of an absorber, okay, trace rho A, for example, is always the expectation value of A. Okay. So I can do this, the trace over the polymatrices, okay, again, expectation value, and that expectation value is your coefficient. And essentially, this lemma of block vector, looking at now, this rho has to be properly normalized. This lambda has to be, this magnitude of lambda has to be less than or equal to 1. So if it's equal to 1, basically you get, essentially what this says is you get lambda 1 squared plus lambda 2 squared plus lambda 3 squared, okay, equals to 1, and that gives you the equation of sphere. But in the case of mean state, where it's actually less than 1, it says that, okay, that particular parameterization of lambda actually gives you a point inside the sphere. So that gives you the idea of a block. So what about qubits? Okay. Yes, well, again, this is not the only one, but no, this is one way of parameterizing it. Again, one just look at a set of Hermitian operators, okay, that that's equal to describe operators acting on this given space D. Okay. So generally, one should be able to find one. Okay, if it's D, then you should be looking at SUV. So you should be able to actually find those generators of SUD, okay, to be inserted into that. So the number of components would be actually is -1. So that means actually there are more components in this. Okay. So actually, okay, the question is how to choose this gamma, which is the Hermitian operator for this d-dimensional Hilbert space. Well, some practical options actually to define this gamma just like a sigma polymetric operation. Okay, and then to choose it in orthonormal in some sense. Okay. Now there are several choices in the literature which follows this parameterization. For example, you can get the idea of German matrices, the idea of polarization operator basis, and the idea of wide operator basis. Okay. The first one is good because it actually gives you the Hermitian operator, but the rest is actually not useful. You can see it. So we look at the Y operator basis because this might be related to things that we probably talk in the future. Okay, so one defines this Y operator basis of this operator space. Okay, in this way, so there's a sum from 0 to d minus 1, so there are d of them. Okay, and there are essentially there are d. So there should be d squared of this. Okay, and we have this phase factor coming in. Okay, and here you have a outer product of this k, okay, with k plus n mod d. So they're supposed to be unitary, and they're supposed to obey the property that we had mentioned before. Okay. And essentially, the kind of block vector representation of this wild vector basis kind of thing like this. And since it's this thing, you can almost immediately see this because you have this phase factor, it's not conditional. Okay? So basically, your block vector components are going to be complex, and there will be some relationship you can of diagonal. So here's the case for the Q-trix, which is given by Guttelman. Okay. So he did also for the Gell-Mann. We also did also the Dr. T. also did for the using the Gell-Mann basis. So just to show you, okay, here are some factors. Okay, so enough said about the elements of quantum information that you want to process. So now we talk about process. Okay. So as I mentioned in the tracing school, that you introduce the idea of unitary operators actually through the idea of change of basis. Okay, but hidden in that statement was actually this unitary operators actually maintain the unit total. Okay. So these are the kind of processes or objects that you want to use to manipulate elements of the quantum mechanics and so on and so forth. Okay. Because you don't want something which is actually losing your probability or something. Okay. So, so you start out with the simple cases. Okay. First, you take the simplest element of information, which is a qubit, and then we talk about a single qubit logic gate. Okay. So we start off something which is familiar to us in classical logic. Okay. We have a NOT gate. Okay. So what it does, it takes a 0, goes back to 1, it takes a 1 to 0. We have the same thing for the case of the qubits. We have this NOT gate given by this. It's normally written as X. 2X. That's a Z. But never mind. So it's actually a polymath. Your X is essentially 0, 1, 1, 0. So when you X on say okay, 0, let's say this is 1, 0. So I can do this kind of representation and do 0, 1, which is okay. So on. So this is the cat right kind of field, right? So you can, from that outer product, some of outer products, you can actually do the values. Maybe you can do that in the tutorial. So what it does is, okay, it doesn't just take 0 to 1, like it's like your classical logic operation. It also takes a superposition. What it does, it flips the 0 to 1 and 1 to 0, and then you still have a superposition. So in other words, you have more things to actually, the kind of operations that you do with synchronous unit gate, it affects more than just 0 and 1. Okay? And this is a Z, this is mainly this is a Z. Okay? And this is not in classical logic, okay? Because you don't have the idea of phase. So what it does is just take the signal matrix Z, signal Z, 1, 0, 0, minus 1. So we add on 1, 0, it doesn't change. Okay? But you add on 0, 1, it requires a minus sign. Sometimes people call this a phase, a special kind of phase. So we start to now, okay, there's a lot more operations that you can actually do with qubits, unlike the case of bits. This is just for a single qubit. Okay? And it's not only that, your ZX operators coming from your polynomial, okay, are just one of the few of the thousands or millions of unitary operators on a single qubit. Okay? So actually you can take any 2 by 2 unitary operator, okay? And it's actually a possible logic gate. Okay? Here's one which is quite important, what we call the Hadamard gate, okay? Which is formed like this. This is actually unitary. Okay? And what it does is it takes this special basis unit, 0, and it maps to a superposition. This is not available at all to your bits, classical bits. Okay? And 1 will be the orthogonal combination. Okay? And just to tell you, can you actually realize this gate? That's a very important question. So you just, if you think that you can just take any unitary operator and then implement this on an experiment, that's not going to be very helpful to experimenters. But this Hadamard gate, for example, how it's actually realized in some linear optic experiment is actually implemented as a beam splitter. So what it does, here's what we call a half qubit. So source here of photons, for example, goes this way. This is a 50-50 mirror. Okay? So you can either reflect or you can actually pass through. So there's a 50-50 probability of doing both. Okay? So you'll be in a superposition state. So that beam splitter for this path qubit is just like the Hadamard gate. So as I said, you can actually take any unitary 2 by 2 matrix and become a single qubit logic gate. But I remember one computer scientist was working on this quantum computation. It's unfair, is it? No, it's unfair to compare classical computation, which you do with bits, and you compare with qubits, in particularly when you have infinite resource in your unitary matrix. Okay? Because you have all these continuous parameters inside your unitary matrix. So really, realistically, you should try to put them in some discrete form. Okay. What Michel also mentioned about Bloch sphere, Riemann sphere. There are similar things in terms of their properties, but here is just to mention the correspondence, how it looks like. Okay. You can actually define a map. Okay. You know that, okay, you can think of box square, particular sphere, and then just do what we call a stereographic projection. So you map it onto a complex sphere. So essentially, what we do is map this 2 by 1 matrix to this Z complex number Z. And here's the interesting thing. So if you can get this correspondence actually can be made exactly unfortunately no. So you think of say a Mobius transformation which is actually acting on this a standard complex plane. Please. Vertex coding. And given by this linear fractional kind of transformation, okay, then you can try to see, okay, can you find the precise logic gate corresponding to some obvious transformation that you know. But actually you can. Here's some example. The Z gate will be just a transformation of Z going to minus Z. And one particular interest looking into this kind of problem to look at the fixed one. Okay. And X gate will be an inversion. And H gate, the Harman gate, will be this kind of linear fractional transformation. But not all Mobius transformation can actually be corresponded to some logic. There are some conditions, because logic gates have to be unitary, whereas this Mobius transformation doesn't have to, so there will be some conditions. Now, can we do more than just single qubit logic gate? Of course you can. And I'm just going to zoom straight away to this idea of control now. Okay? So, what is it called control? First of all, okay, it's a 2 qubit, that makes it maximum 2 qubits, here's A and B. And then, process it with this thing, whatever that means at the moment. Okay? And then you get an output of 2 qubits. Okay? So what it does, it has this kind of property. If A is actually 0, B can be anything. Okay? So your first qubit, which is actually what we call the control qubit, okay, will just goes through unaffected. So the control qubit stays the same, but the target qubit, so B, okay, if it's 0, it also goes to B. Okay? But if your B is actually a 1, okay? Sorry, if your A is actually a 1, okay, then the target qubit can actually change according to this operation. This is addition not 2. Okay? So in other words, if it's a 1, it can flip the 1 to 0, the 0 to 1. Okay? So this, you can see this like a not gate. So in other words, it's like you're having always thinking, as I mentioned earlier in the beginning of the lecture, quantum information kind of field is actually it's not like a physics field. It's a study about nature. It's an engineering field. Okay? You want to engineer to have control. So if you want it to be unaffected, it was control qubit 0. If you want it to be affected, so then it's 1. And this control not qubit is the only thing you need for a 2 qubit logic. Because they actually proven that your synapse gate is actually universal. So you can start, generating other kind of processes. So, okay. So in other words, you have now logic gates, just like logic gates in computers. So you are, by right, you are able to do computations. So there are two models of quantum computing that is possible. One is what we call quantum circuit model. And in this quantum circuit model is that the number of input qubits is always the same as the number of output. And before you measure the output, all processes are actually reversible. Remember that your unitary matrices or gate, they have inverses. And what you want to do is to concatenate, join up all these logic gates for your desired process. Okay? Here's a circuit diagram. I'm not going to go into it because this is a lot of details. Basic idea of this lecture is just to give you ideas of algebras or algebraic structures which will come to play. So here's a circuit diagram for Shor's algorithm. Shor's algorithm is the one that gives quantum information field research area, the boom, because it's an algorithm that tends to be able to factorize large numbers, prime factorization. And prime factorization is the one being used to do cryptology stuff. So if I have a quantum computer that actually implements Shor's algorithm, that means I can actually break any crypto system because this Shor's algorithm actually is an efficient algorithm to factorize prime factorized numbers. Okay? So I can actually break any particular crypto system that's based on this prime factorization. If you want to, it's pretty complicated. We have more. There has this Hadamard gates. So operating on the qubits, okay? And then it has this idea of what is called this quantum Fourier transform. So these are the kind of things that people do. And here's this meter-looking object stating that that's your doing measurement. Okay? So you can start drawing this kind of diagrams. Okay? That actually becomes an algorithm. That is surprisingly, comes as a surprise. There is another kind of quantum computing model, which is what we call measurement-based quantum computing. Okay? So it starts to have it prepares a state which is highly entangled in some lattice, for example. Okay? Prepare the source of the state, and then it starts making the measurement on the qubits from the vertices of the lattice, for example, okay? And then we get the design computation. And they claim that this measurement-based quantum computing can always be realized as a quantum system. So in other words, there's some equivalent. But the only thing is that let's suppose I know a quantum algorithm, I know a quantum circuit that implements that, and I know what the source cluster state. That is not known. Okay. So I have another 10 minutes. So here's the quantum communication part. Last slide. Here's some of the things that we're going to do is to actually communicate certain quantum states across. Okay? And this is one process for quantum teleportation. Okay? That actually does. So here's the circuit diagram. Okay? If you want, we can actually do exercise on this. Let's say, okay, I have an unspecified qubit that I want to transport across. Okay? And I couple that with this what we call Bell state. Bell state is given by this entangled state, which I shall mention before. But now this entangled state essentially there's correlation of the first qubit and the second qubit in the states. Okay? Which is not knowable in the classical sense. Okay? So you couple this psi with beta naught. How do you couple? In terms of maths, it's just simply a tensor product. Okay? So psi tensor product beta naught. Okay? So you get the initial state. Okay? Maybe you can do this for tutorial. Marisha, we do this for tutorial. So we have this initial state, and you perform a control knot gate, okay, based on your unknown qubit and your entangled qubit, okay, and then do a Hadamard transform. Okay. And after that, that's it. That's measured. So you can measure that, okay, this the thing that is done by one party. Okay. The measurement is done by one party. Say Alice, Alice. Why so and then once Alice has the result, okay, you will actually communicate with God what the result. And she knows what she measured, the measuring operation. Okay? And communicate the result to Bob. And then Bob will actually know what measurements we mean by Alice. So then this Alice and Bob has to communicate. Okay? In a classical sense. Okay? And then Bob will start doing some operations according to what this M1 and M2 result is supposed to be. Okay? By doing so, okay, one will be able to reproduce this side and this side. So Bob gets the unknown state. Okay? Alice does not have to know what side. So all this process you can actually try to find out, okay, at this juncture is your initial state, psi naught. At this juncture, after doing a control knot gate, you have psi 1 state. At this juncture, you have done Hadamard gate for the first qubit thing. And then you do a measurement, okay? And then communicate the result. And basically, Bob will do a measurement. So that actually will actually demand the So in other words, something will get destroyed when you measure. Okay? So it's not something that it's not like a stuff. Okay, so these are some references. Again, sorry to finish a little bit earlier.
If you go back to the previous slide, you know the references, the 0, 0, and 1 for the So like 00 represent would the entirety represent just Alice or Alice and Paul?
The entire pair will be shared by everyone.
So it's 4 over 1, so it means like it's
Let's say that the first one is the one that Alice goes to. The second one is the one that goes to Paul.
Okay. And 0 represents what percentage represents is it? I
No,
don't
it's just the state of that entangled unit. First unit.
I don't know.
So that means if it's just this state, if Alice measures 0, that means what will definitely measure.
Oh, this is right. Okay.
And tomorrow now, one actually is why we call this angle.
Yes.
Any other questions?
Clarification of Sean vibration about the hop vibration.
Vibration. Oh.
Because I think what is it? Because I just saw that.
Well, it's a matter of idea. It's not really physical. It's just a way of. Yeah, it's okay. I mentioned about the CP1. CP1 is actually, topologically the same as 2, and you can find those up to S3, okay, by including some fibers in 1. U1 is actually S1. You have this nice structure of operational sphere. And the way they stick the fibers as 1 is not just simply sticking it. There's some kind of a way thing. You can look up the YouTube or something like that. Actually, show how to simulate this. So it's a non-trivial kind of sticking fibers. And easy example of fiber bundle is the idea of, maybe I start with a cylinder. Okay, I have a cylinder S1 really, okay? And then I take the tangent to this point of this S1, okay? Okay? But rather than drawing the tangent should be in that sense, so put fiber up, okay? So you can something like this. And essentially what you get is a cylinder. So that's a fiber bar. Okay? But now you can have something a bit more weird. You probably know about the Mobius strip. The base space is still S1, sorry. Okay? But now there's a twist. So that twist has to be there to make the vibration non-distinct. Otherwise it's a product distinct. Okay? So this CPN can always be extended to some one real dimension to scale. And this can be thought of sticking phase vectors here. Look at him.
So in the generalized spot vibration, right, falling from the first equation of the symmetric space. So this is just 0.
No.
And oh, because in this vibration of CPN, I'm thinking about the first equation that you gave on the symmetric space.
No, this one is for CPN. This one is actually okay, the vibration here is at U1. It's just some, if this is CPN, you multiply U1, okay, then you get your people. So
On the second question, and on the second, so we can only operate on this step.
and there are people are studying these kind of things and then trying to look at some subspaces and you start thinking of space optimization. Okay? And then you look at the local unitary orbits of that space. And you might say something about
This
that.
is which of the operate this.
It's not just for U1, right?
This operation for this one is actually
Only for
because
That's what it's called.
that's the construction that we told you. Okay. I don't know whether they have started thinking about putting other fibers. But no, certainly the one that we call hot vibration, the one vibration.
So the one is 0.